So welcome back, and welcome to actually a new topic. And this is actually a topic which we have postponed quite a lot. And if you go into many courses in quantum computing, basic courses, what you will see is that the quantum Fourier transform comes quite early. Now, we have postponed it till now, essentially because we wanted to emphasize the variational quantum eigensolver as a way to solve many body problems. And this algorithm has been the last 10, 15 years, 10, 12 years, and it was presented in 2014, has been the kind of standard way to solve many body problems on quantum computers. However, historically and from the very beginning, there was an algorithm which is called the quantum phase estimation algorithm, which is actually based on quantum Fourier transforms. And quantum Fourier transforms is actually a extremely nice algorithm, which we are going to discuss. And it lays the foundation for more advanced algorithms like Shor's algorithm, the quantum phase estimation algorithm, and many, many other ones. So it's a very important set of algorithms which we are going to discuss now. And also when we come to quantum machine learning, this becomes a very important, we could almost call it a kitchen ingredient. So it's a basic ingredient which we need to understand. So the thing which I wanted to start with, however, I'm going to give you a kind of motivation how this fits into the basic machinery in this course. I also wanted to mention that next week, I'm going to present different options for the second project. And many of you have been working more alone. And so if you're interested in teaming up with people, please let us know. And I know that some of you here would like to team up with people for the second project. So this is something which we can also discuss next week. But I want to give you a kind of motivation because I know that many of you have not seen Fourier transforms. So how many here have actually gone through the mathematics of a standard Fourier transform? One of you, okay. So I hope you don't get offended if I repeat some of the basics of Fourier transforms. And there is also a variant of the Fourier transform which is called discrete Fourier transforms. And this leads to one of my other favorite algorithms. So I have mentioned the singular value decomposition. And then for those of you who have done computational physics, you probably encountered Metropolis algorithm. But then we have the fast Fourier transform, which is also a great, great algorithm, which actually sped up the calculation of discrete Fourier transforms. So I will try to motivate a little bit where these Fourier transforms arise, and why they are so interesting. And in quantum computing, it's an essential algorithm in many, many other algorithms. And we are first today, we are going to look at the basic mathematics of it. And we can actually rewrite this as unitary transformations acting on a state. And you will see the same when we deal with a discrete Fourier transform. But then we are going to translate that, instead of looking at matrices, we are going to translate that into quantum circuits. And this is a very efficient way by which we can actually simulate a quantum Fourier transform. Now, the quantum Fourier transform is also an algorithm which is central in this quantum phase estimation algorithm. Have you heard of that one? QPE, some of you heard of it. And this algorithm was actually one of the first algorithms which was presented to find the eigenvalues of a given Hamiltonian. So one variant of project number 2, I just wanted to mention that, is to implement the quantum Fourier transform and the quantum phase estimation algorithm and compare those results, which you get with that on a given Hamiltonian, with those which you have from the VQE in project 1. So that's a very well-defined path for the second project. So you would then stay within the Hamiltonian system studies, but where you're going to use another algorithm. Now, the quantum phase estimation algorithm has lost a little bit of the steam compared with the VQE because it normally gives very long quantum circuits, which means that in the era which we are now, where you still have a lot of noise in quantum circuits, the coherence plays an important role. Then the QPE, the quantum phase estimation algorithm, is a little bit, I would say, it lost a little bit of its actuality compared to the VQE. Okay, but it's for us who are just confined to running things on our laptops or PCs, this is actually a very good exercise. So, as I say here, Fourier transforms is something you can view actually as a standard kitchen item almost. So I'm going to go through a lot of the mathematics today. I'm not going to show much code except some few examples. So it's the quantum analog of discrete Fourier transforms, and I will try to explain to you why the quantum Fourier transform give a computational advantage compared to a discrete Fourier transform and even the fast Fourier transform. So that's a very important aspect, because Fourier transforms, as I said, play a very important role in many scientific applications. They play a crucial role in Shor's algorithm. So if somebody is interested in project 2 to actually work on Shor's algorithm, we had a group last year who did that. You actually need the quantum phase estimation algorithm and the quantum Fourier transform. So it's as I said, you will see this popping up as a basic kitchen item. And they provide an exponential speed up over classical Fourier transform methods. The classical discrete require typically n squared operation. The fast Fourier transform actually reduces this to n log n. And then the QFT reduces this to an even smaller when you use quantum gates. So there is a considerable advantage in these type of calculations. So you will see now that what we are going, so if you do a QFT on 1 qubit, that has a very simple quantum circuit. It's a Hadamard gate. And we will see that even when we do the discrete Fourier transform for 1 qubit. So it's actually a set of states which is superimposed. So if you think of a Hadamard gate, that's a superposition of bits 0 and 1. When you have 2 qubits, you will actually have a quantum Fourier transform, which is a Hadamard gate plus a rotation gate. So when we implement the algorithm, you can translate the mathematical operations which you would do in a fast Fourier transform with matrices. You would then just implement that in terms of quantum gates. So, and you would then process all inputs simultaneously. So the quantum Fourier transform is an example of what we call quantum parallelism, because you have a superposition of states. But when you make a measurement, you obviously collapse one of the states. So it's crucial in algorithms like Shor's and quantum phase estimation, as I said. They require only Hadamard gates and controlled phase gates. So these are the only gates which are needed. And we will see later today the number of operations which we need, where little n here is the number of qubits. So quantum Fourier transforms are very efficient for quantum hardware. And as I said, these are the fields where you will encounter it quite often. So Shor's algorithm I mentioned already, quantum phase estimation, quantum signal processing. It's also expected to be very important for quantum machine learning. I think I already said this. Yeah, let's just skip some of these here. This is just a little bit repeat of what we said here. So what I want to do now, so I'm going to use slides a little bit in the first lecture now, and then we're going to jump into the whiteboard when we look at the quantum Fourier transform and how to set it up. So for those of you who are less familiar with Fourier theory, you may have met this equation here. This is a famous equation for damped motion if you take away an external force. So f of t could be an external force of the system. It's often called a driving force. And you can use the theory of Fourier transformations to actually find the solutions to this type of equations. Has any one of you seen this? If you've taken a course in mathematical physics, you can actually solve this type of differential equations by using Fourier theory. That's a common way of actually dealing with the equations, which in particular have periodic and continuous functions. So f of t could be a periodic function. If you think of the pendulum you have in the entrance of the physics building, that's actually an example of a pendulum which swings back and forth. And without an external force, it would have come to rest after some time due to air resistance, friction, etc., etc. So if you have several such driving forces, you can find a particular solution to the above differential equation for each of these forces. And then the particular solution for the entire driving force is given by a series like this. And this is known as superposition. So superposition is not a quantum mechanical feature only. You have superposition in classical solutions as well. So especially if this can be written as sinusoidal terms, then you can actually really exploit the whole machinery here. And the other thing which is interesting for many of the situations here is that driving forces, they are often periodic, even when they're not sinusoidal. And you will see that if you take a box potential, no, what is what's called now again? I'm going to show you that. I'm forgetting the name of that type of signal. A square wave signal, sorry. That's a typical example of a periodic force which you can apply on a system. And many components in electric circuits, for instance, are nonlinear, for example, diodes, and this makes many waveforms non-sinusoidal, even when the circuits are being driven by purely sinusoidal sources. So if you now look at Fourier's idea, it was actually, the idea was to expand a continuous and periodic function in terms of sums of sine and cosine ordered functions. And in this specific case, what you have is an expansion of a function in terms of sine functions. This phi of n is normally called a constant phase. And the function is assumed to be bounded in order to be able to define properly the error in truncating the sum over n. So that means that if you integrate this function, it should not diverge. And what we are going to look at now is just a basic reminder on how you find these coefficients a of k. So if you look at this, this is nothing but you taking a basis which is orthogonal. So sine and cosines are orthogonal functions. And we are simply expanding a function here in terms of an orthogonal basis. And then the whole thing is to find the coefficients a of k. So typically what you would see is that you would rewrite the above sums, this sum in terms of sines and cosines, and you just add a complex constant. And then you can, here we actually use the standard trigonometric relations. So this is often a form which you will encounter in textbooks on Fourier theory. So if you're dealing with signal processing, if some of you has taken courses in that, then Fourier transforms would be often, or Fourier theory would often be the theme for a whole semester in signal processing. And you can rewrite the Fourier expansion in terms of the standard exponential. And then in this case, the C of k's are complex numbers, and the C0 is a real number. You can also rewrite it in terms of the real part of the exponentials. So this is just playing around with the mathematics of cosines and sines. So I hope I'm not abusing too much with slides, but I just wanted to remind you quickly about some of the basics. If you have a periodic function like this f of t, and you select these coefficients and you multiply the left-hand side and right-hand side with the exponential here, and you isolate this CL term, you can then actually find an expression for the CL term. So if you take the previous expression like this one, and you multiply it with the exponential with minus 2 pi I, then you can actually isolate a specific coefficient. And this is actually at the root for the algorithm for finding these coefficients. So then you can integrate both sides. So in this case, I've just scaled everything so the period is equal to 1. So I integrate from 0 to 1, and then you have an expression for these terms here. And these terms, they are normally called the Fourier coefficients. And it's common to relabel them in terms of a function f. And this is a kind of relabeling which I will also use during the lectures here. So this gives you a recipe to find the coefficients. So if you think of an expansion of a quantum mechanical function in terms of a basis, these CLs are just the overlaps between your function and the computational basis states. Nothing but that. So that's another way of thinking of it, except that now we are explicitly hard-coding sine and cosine functions. So you would then typically label this one in terms of an F. And it's important also that when you integrate, instead of having a period of length 1, like you saw here, you could have a period of length A. So you would integrate typically from A plus 1. This is the same as integrating of an interval of length 1. And you can actually show that if you, when you require that you have this periodicity, so after one period, then you should recover the same function. So this is one of the requirements which you impose. And later you can actually generalize this to a period of arbitrary length. So it's pretty easy to see this, because if you take the derivative of the previous function, which you had here, with respect to this variable a now, instead of integrating from 0 to 1, you can now integrate from a to a plus 1. And if you do that, you can then quickly show that if you use the periodicity and that the exponential of 2 pi I times k is equal to 1, since k is always an integer, then that shows that the expression for this is actually independent of this. And a common approach is actually to redefine it, where you integrate from -1/2 to +1/2. Or you can change the period. Another alternative is actually to if the period is not equal to 1, you can actually, by simple manipulations, so if you have a period which is just t, uppercase letter t, then you can define a function with period 1, which is simply given by t times little t. And then you can manipulate things properly, introduce a variable s. So these are just the small manipulations. And at the end, you can actually redefine everything. This is not very exciting, but I'm bringing it up because I wanted to just remind you of some basic elements of Fourier theory. But this would typically be the recipe you would use to find these coefficients. A choice which is often used is actually this one. And a common choice for these harmonics is actually to use this expression here. So these are just some small trivialities which I'm adding here. And for the example which I showed you, where the period is 2 pi divided by omega, where omega is the frequency, then you can also rewrite everything in terms of a sum of these so-called harmonics in terms of cosines and sines. And then the whole quest is actually to set up the recipe for finding these a's. And there's a code example which I'm going to show you in the Jupyter notebook, where I'm actually taking a square well. So let me just do that first. And let's stop, because what I'm setting up here, let me just bring this up. Not that one, but this one. No, this one. Yeah, here we are. So one of the examples which I have in the slides here is a very exciting signal. This is the typical square well signal. Now, you're going to notice something here, because the function is discontinuous. And we are trying to fit a discontinuous function with a continuous function. So if you look at this function here, this function is something which we can, if we scroll down a little bit and go back to the material we had in the slides, this is the square well example, where we have an f of t, which is either 1 or -1 in these intervals. So the example which you saw is essentially this as a signal. And we can set up an integration over 0 and 1. And you can find the coefficients, the analytical expressions for the coefficients, when you now plug in this formula for the Fourier transform. So we would simply be integrated from 0 to 1. And this case has actually an analytical function, which you can encode easily. So this will be the coefficients. So that means that as soon as you have these coefficients, you can then set up an expression for the square well wave signal. Because then you have the coefficients f of t, and f of t is now given in terms of, so if f of t is your square well, then you can express that one in terms of these sine functions here. If you do that, this is actually a code where I have implemented it, and you will see now that with the 500, so what I'm doing here, this 500 in this range, I'm actually making a sum because I cannot run to infinity. I sum up to 500, to n equal 500. If I were not to do that, suppose I just do 50, you will notice one thing quickly, and obviously it will look like this. So at the corners here, where the function is discontinuous, we are trying to approximate a continuous function to a discontinuous function. So that means in principle, if we want to get a good representation, this k has to run over many, many values. So if I increase this now to, instead of 50, I do 500, then you will see that on the resolution of this scale, you will see now that it looks almost like a square well. But if you were to enlarge the corners here where you have a discontinuity, then you would clearly see that there are some wiggles here. And you can see that even with 500, if you narrow it down here, you will see that the corners are not properly reproduced. And you will see here down here that actually this tends to be a continuous function. So you need a huge series of sine functions in order to be able to approximate a square well, which is a discontinuous function. But anyway, this is a typical recipe, which is then used to approximate periodic functions. And Fourier theory plays a central role in, let's say, signal analysis. Is anyone here taking a course in signal analysis? It's a common course at the Department for Informatics. Next year, okay. And then actually, if you do signal analysis, Fourier transforms and Fourier analysis is a basic building block now. So you will then most likely have at least one half of the semester will be dedicated to the mathematics of Fourier transforms. You're warned now. Now I really find that it's a topic which I've always been very fond of, Fourier transforms. So let's go back to the slides, because I wanted to expose you to a little bit more about Fourier transforms, etc., before we switch to the whiteboard, so that we have a kind of basic common mathematics, and you can say this is roughly what we have. I just wanted to give you some additional mathematics. So we would normally define the inverse Fourier transforms of a given function g of w, which is then given simply by this exponential here, multiplied with the function itself. And the inverse transform of the product of two functions is actually given by this expression. And you can rewrite the latter in terms of this function here, which is actually the convolution of f and g. So that's another just technicality. So if you do the Fourier transform, so the C of n is transformed from a discrete variable to a continuous one as this t goes to infinity. And that means that you replace, let me just switch off the sound here. Yeah. So that means that you replace this C of n with fk of dk, and you let this n over t, the period, go over to k, and then the sum is changed to an integral. And that gives us this expression here. And one way to interpret the Fourier transform is then as a transformation from one basis to another one. And you will see that explicitly when we switch to discrete Fourier transforms, that this is just going to be a unitary transformation from one basis to another. So I'm going to skip some of this, but I wanted to now define what is called the discrete Fourier transform. Okay, so let's now switch to the whiteboard because this is now time to do so. And we are going to look at the discrete Fourier transform for some specific examples. So how many of you have seen discrete Fourier transforms as well? Okay, 2 of you have, okay. So let's take a look at the mathematical definitions of that. And now we are going to switch to the whiteboard. So if we look at, if we have a vector, so we're going to start with the discrete Fourier transform. And the way we have written a vector is in terms of the standard bracket notation. So you could think of a vector x0, x1, these are the different components of the vector. And then we are going to make a transformation to a new basis. So we are going to find a new vector y, which is given by some transformation multiplied with x. So a Fourier transform, if we now look at the discrete variant, is nothing but us finding a unitary transformation which maps the original vector x to a new vector y. Okay, this is the basic mathematics. And when we are going to look at quantum Fourier transforms, it's essentially this expression which we are going to take into account, except that we are not going to deal with matrices, but we're going to set this up in terms of quantum circuits. And the quantum circuits are going to be Hadamard gates and rotation gates. So we can actually translate this operation here in terms of, instead of a matrix which multiplies our original vector, in terms of quantum gates. And that's the way we would implement this on a quantum computer. If you look at the codes which you have at the very end of the Jupyter notebook this week, the first code actually sets up the Fourier transform by just taking a matrix U and sets that up and performs a matrix vector multiplication. And then you can test that your matrix is unitary, etc., etc. But the next code, which is at the very end, translates everything in terms of quantum gates. So let's take a look at the mathematical expressions here. So in principle, these xj's, they are complex numbers. And if I look at one specific component, if I now look at this vector y, this is going to be given in terms of the specific components. There will be a y0, y1 down to a y of n minus 1. And one specific component, which I'm just going to label y of k. So this is the mathematical definition of a standard Fourier transform. This is actually given by a discrete Fourier transform, 1 over n, square root of n. And then I have a sum from j equals 0 up to n minus 1. This is multiplied with xj. And then I have e, and now I'm setting up the Fourier transform. So 2 pi times I. And then I have j multiplied with k divided by n. And this is the basic expression which we have. So if I look at this specific vector y, the different components then will obviously contain 0 first. So if I have k equal to 0, that means that this one is just going to be e to the 2 pi I times 0, which is obviously 1. So that's pretty easy. And then the other ones will then depend on the values of k here. So let's just look at what this vector, this new vector, is going to look like. So let's just write it out in terms of the mathematical formula. So this is just the expression for a discrete Fourier transform. So if I write this vector y in terms of the different components, there's going to be a 1 over square root of n, and then I can set up the different components here. So one of them has a sum j equals 0 up to the coefficient. So xj are the components of the original basis, which we are now transforming. And then I have e to the 2 pi of I, and this is given by j multiplied with 0 because k is equal to 0. So let me just mark that one. So this is the case with k equal to 0. That's the first component, y0. And then I should put a parenthesis end here. Then I have the next one, which is j equals 0 up to n minus 1 of xj of e to 2 pi of I. And then I have j times 1, because k is equal to 1 in that case, divided by n. And this goes all the way down to the last one, j equals 0 to n minus 1. And then I have xj of e to the 2 pi I. And then I have j multiplied with n minus 1 and divided by n. So this is the classic discrete Fourier transform. And this could just be the components like we wrote down here. These are the components of that vector x. Now, we are going to later translate these x's and the y's in terms of the computational basis with qubit 0 and qubit 1. Okay? So this is the translation which we are going to do from the classical one. So what we are setting up here is nothing but the discrete variant of the continuous Fourier transform, which you saw me rushing through quickly in those slides. Okay? So let's look at an example. It's useful to break it down. And when you look at this example, you can actually rewrite this one. Suppose now that we have, and this is going to be exactly the same if I look at a 1 qubit case. And you will see that later. So suppose now that this vector is just given by a simple expression, 1 and 2. So this is essentially the vector, which is now x0 and x1. Okay? Now, since these are unitary transformations, we all have to preserve the size of the vector. So that means that the new vector has the same dimensionality. So we will have a y, which is given by y0 and y1. So these are the two components. And that means that if I take y0, which corresponds to k equal to 0, and then I go back and plug that one into the formula here, so I have two components. So I have x, which is 1 and 2. So what I get then is that this is equal to 1 over square root of 2. So this is the term, the first term, we have e to the 2 pi I, j times 0. So this gives always 1. And then I have to divide it by 1 over square root of 2. My second term, when j is equal to 1, is given by 2 here. So this is equal to plus 2 divided by square root of 2. Okay? So that's the first coefficient. And then I take my y1, which is the same as k equal to 1. And now I plug that one in. Then I have 1 divided by 2 plus 2. So this is actually me plugging in x0 there. And this is x1. And the same goes in here. And the same goes in here, divided by square root of 2. But now I have to be careful because if I look at my exponent, I have I times pi. Because in this case, j is equal to 1, 1 times 1, and I divide by n, which is equal to 2. So then I get e to the I pi. which we know is equal to -1. Now, if I then look at what I've done, if I take the vector y, and we even use this quantum mechanical notation for a classical vector, this is the same as u times x. And what you will see now is that u, in this specific case, is equal to something you've seen before. 1, 1, 1, and -1. So if you think quantum computing, what do we call this guy here? It has its own name, actually. That's a Hadamard. So what you see now is that this specific case where we have two components, when we now translate this into, instead of 1 and 2, two given values, which we now transform into a new basis, this is given by a unitary transformation where we have a Hadamard. That means that if we replace 1 and 2 with qubits 0 and 1, we would then have a Hadamard transformation on 1 qubit. And we are going to see that when we look at the quantum mechanical variant. Okay. So keep also in mind that we have already demonstrated this, that this matrix is unitary. And for the Hadamard gate, it's pretty easy to see, and we actually done it. So the thing is that this classical DFT, this can be the speed up of that one. You see now that if I am going to look at the, let's say, 4 components, this would be a 4x4 matrix. So if the vector here has 4 components, instead of a 2x2 matrix, you're going to get a 4x4 matrix. And these matrices have actually an analytical expression. And this analytical expression is something which I will set up pretty soon now. But the thing which is interesting is that if we look at what we have here, this is a unitary transformation. When I implement a DFT in its classical way without a fast Fourier transform, this is essentially a matrix times a vector. Okay? Now, if you implement it without any concerns about speed, if the matrix has dimension n times n, the number of floating point operations which you typically end up with here is something which goes like, and now n is the size of the matrix. It goes like n squared. Now I should be a little bit careful here. I'm going to change the notation because later I'm going to use little n for the number of qubits. So in this specific case, U is a matrix which is assumed to be complex, which has dimension n times n. If I don't do anything, then the standard discrete Fourier transform is a matrix times a vector, and that requires roughly this amount of floating point operations. If I do a fast Fourier transform, you can actually show that this reduces to n times log n. Now, we are not going to discuss the algorithm for fast Fourier transforms because that would be at least another two lectures at least to introduce the algorithm. So I'm just stating that, okay? So if I do a fast Fourier transform for FFT, this goes like O of n times log n. So that's a considerable speed up compared to just a brute force multiplication. So what we have is a type of expression which we could, in a way, think of is pretty generic. So if you look at this one, there is a kind of a similar example. So let me just put it up. And then later I'm going to set up the matrix which you're going to encounter when you do a normal Fourier transform. So think of a digression like a polynomial expansion, just to see some parallels to what we are doing. So this is just meant as a small digression. So if we do a polynomial expansion, what we are doing then is to have function which we are approximating with a polynomial of a degree n-1 evaluated at points x of I. And we know that that one is equal to j equals 0. This is also a case which we can rewrite like a matrix times a vector. So in that specific case, what we have then are some unknown coefficients, which are then multiplied with x to the power of j. And we know that this one is equal to a0 xi to the power of 0 plus a1 of xi. And this goes all the way up to an-1, the coefficients of xi to the x to the power of n-1. That means that I can define a vector f, which now contains these polynomial degrees. So if I define this vector, this is going to be given by these different components, p of x0, this is the polynomial I've chosen, x1, all the way down to p of xn minus 1. And I can actually rewrite this as a matrix V times a vector A, where these A's are the unknown coefficients, A0 of the polynomial, A0, A1, etc., of the polynomial expansion. So this V is actually given by 1, and we have 1 along the columns here. And then we have x0 to the power of 1, x0 to the power of 2, of x0 to the power of n-1, and x1 to the power of 1, x1 to the power of 2, and x1 to the power of n-1. And this goes all the way down to xn minus 1 to the power of n-1. And this vector A is nothing but these unknown coefficients A0, A1, down to an-1. So what you have here is actually a linear algebra problem, because typically you would know these values of the function. You would multiply with v minus 1 and you would get these unknown coefficients. This matrix in polynomial approximation theory has a name, and it's called van der Monde matrix. If I look at my DFT, I get something similar. So we get something similar with DFT. So I'm just going to set up these different coefficients with DFT, then discrete Fourier transforms. So if I define this coefficient of omega as e to the 2 pi of I divided by n, okay? This is just a common factor in the Fourier expansions. What I will find then is that this x01, which I have, is actually equal to e to the 2 pi I, and then I have 0 times 1 divided by n, and this is equal to 1. I would get x02, which is, if I want to make a comparison with the polynomial expansion, and then I have 2 times 0 divided by n, this is equal to 1. So all the x0s are actually equal to 1, as we had in the van der Monde matrix. But then if I take x1, this is the same as e of 2 pi I divided by n, and this is the same as omega. So I'm just setting up the standard expression for the Fourier transform in terms of these coefficients, which we set up before. And then you will see that these different terms, x1 squared, e to the 2 pi I, and then I have 2 times 1 divided by n. This is the same as omega squared, etc. So when I plug in everything here, what I'm going to get is that this unitary matrix, which I'm going to get, this u, is going to look like as 1 over square root of n. So this is for the discrete Fourier transform. I have 1s here all the way. And then I get 1, and then I get omega, omega squared, omega cubed, all the way up to omega of n minus 1. This continues, and I have omega squared, omega to the power of 4, and all the way up to omega of 2 times n minus 1. And this goes all the way down here, and we have 1s, and we have omega of n minus 1. And this goes all the way up to n minus 1 squared. So this is the transformation which I get when I'm setting up the discrete Fourier transform. And the discrete Fourier transform is given by us mapping this y of k, a given coefficient, which is 1 over square root of n. There's a sum over j equals 0 of n minus 1. And then I have an xj of e to the 2 pi I, j times k divided by n. So the thing I've done now is simply to set in the explicit expressions for this matrix U. So what I would get then is U is equal to Y is equal to U times a vector X. So this is the discrete Fourier transform. And you saw an example here of the case with just 2 elements. And that gave us the Hadamard matrix. The general expression for the discrete Fourier transform is then given by something which looks like the one we had for the polynomial approximation, except that now the matrix element is given in terms of these parameters omega, where omega is e to the 2 pi I divided by n. So this is nothing but us setting up the expression for the transformation y in terms of the given components yk, which then relate to the original basis x. So the discrete Fourier transform gives us a way to transform a basis to a new basis. And we could rewrite this in terms of a matrix times a vector, or we could implement this in terms of a fast Fourier transform. The thing I wanted you to keep in mind is also that this matrix U is unitary. It preserves orthogonality thus. So if I look at a specific vector y and I transform that one, I will see that if this x is orthogonal and normalized, it will keep orthogonalization and it will keep the normalization. So that's a very common feature of unitary transformations. So after the break, we're actually going to move from this expression you saw here to a quantum Fourier transform. And that's what we will do after the break. Okay? So, but the basic expression which you see is this one, but we are going to translate these n's which you see here in terms of a given number of qubits. And then instead of performing a matrix vector multiplication or fast Fourier transformation, we are going to implement this on a quantum computer in terms of specific gates and operations with gates. Okay, so that's a kind of overarching thing. So just to conclude, and I went a little bit over time as usual, but I will give you back 5 minutes. So we will end in time at 12. But what I wanted to stress is that even if this looks very technical, what is of interest for us is that this quantum Fourier transform enters as a kitchen item in quantum algorithms like Shor's algorithm, the quantum phase estimation algorithm, etc. Okay, should take a break. So I'm gonna put on the pause the recording. So before the break, we looked at the discrete Fourier transform, which we then can simply rewrite in terms of a unitary matrix multiplied with a vector. So this transforms our state from x to y. And this is the way we can actually rewrite the standard discrete Fourier transform. Now, I just mentioned that the transformation is unitary. And in a unitary transformation, that preserves orthogonality. So if we have an original basis, let me just quickly remind you of that, if you have forgotten it. Suppose that we have an original basis, which is orthogonal. And then we know that if we make the transformation and we look at the new basis, this is obviously given by, sorry, the new basis. So that would be a y of j. This is the same as x of I multiplied with u and xj. This is by definition equal to the identity matrix, so this is equal to delta ij. So the orthogonality is conserved. Now, what we are going to look at now is the case where n, which previously meant the number of basis states. So n is the dim of x and y. That means that the matrix U is a matrix which we assume to be complex, which is of dimensionality n times n. Now, when we introduce qubits, this n is actually going to be given by 2 to the power of number of qubits. So with qubits, what we are going to have then is the following. So n is going to be given by 2 to the power of little n. And little n is the number of the qubits. Okay? So let's look at an example. And the obvious case is actually that of n equal to 1. So that means that n is equal to 2. And in our case, that translates into qubit 0 and qubit 1. Okay? So this is our basis. That means, again, that if we now take the Fourier transform, what we are going to get then is a new basis 0 and a new basis 1. So it means that we could now look at a transformation of a new vector y, which will have a transformed vector 0 and a transformed vector 1. So which is given by u times this vector x and the original x. So that means that I would get something which looks like this now. So x is now given by qubit 0 and qubit 1. So when I perform the transformation here, what I'm going to get is the following. So I'm going to get a 1, it will be a 1 over square root of 2. So 2 is the number of total states which I have, the length of it. And then I'm going to have a 1 and 1 minus 1. And this is multiplied with the states 0 and 1. So if we look at the what we might call, so let me just keep this one a little bit. So this is actually the Hadamard gate. So let me just rewrite it in a somewhat strange way. So I will have a 0 state or 0 tilde, which is actually the 0th component of the new vector, which is going to be given by 1 over square root of 2. And then I have a sum from k equals 0 up to 1. And then I have a e of 2 pi of I of 0, because we have 0 here, multiplied with k divided by 2 and k. So when I write this out, this is going to be equal to 1 over square root of 2. And then I have e of 2 pi of I times 0 times 1. No, sorry, 0. Divided by 2, and then I have qubit 0. So this is obviously equal to 1, the first term, plus, and then I have 0 again. So this is simply 1. So that is going to be given by 1 over square root of 2, and then I have qubit 0 plus qubit 1. So this states, which you see now, this k here, is actually one of either this one or this one. And if I take this 1 tilde, this is now given by 1 over square root of 2. I'm going to get 0 still here, just qubit 0. But then I will have plus e of pi of I multiplied with 1. And this is the one which gives us simply 1 over square root of 2, qubit 0 minus qubit 1, like that. So now I'm just writing it out in full detail. So if we want to translate this into a quantum circuit for just 1 qubit, this Fourier transformation which we have here, which we have written mathematically like this one, is now going to be given by simply having a state X here, which then gets transformed by a Hadamard gate, and then we end up with a state Y here. So this is a 1 qubit circuit for the quantum Fourier transform. Now you can obviously do the matrix-matrix multiplication, the matrix vector multiplication, but this is something which becomes less practical, and the origin for the advantage of quantum Fourier transform compared with the classical ones is simply the fact that we can break down this in terms of gates, and that reduces the number of operations considerably, and we will see that next week. So let's now look at another example. And since we started with 1 qubit, then the next example has to be 2 qubits, okay? No surprise. So this is the example 2 here. And now we are going to say that n is equal to 2 qubits. So this is the number of possible states. And it means that we have 2 qubits. And in our case then, so I'm going to introduce a notation here. And the whole trick, which you will see pretty soon, is to be able to rewrite this Fourier transform. So in the case of 1 qubit, things are pretty straightforward. But with 2 qubits, what we are going to see now is that we can actually rewrite this in terms of tensor products, where we have the computational basis of qubit 0 and qubit 1. So this is the way we are going to map this now. But let's introduce some further technicalities. So if you look at the vectors y now, so this vector y, which we have, is now going to contain 4 components. And the 4 components which we will have, and this applies also to the vector x, so we can write both of them, and they will just be linear combinations. So what we are going to have is that y is now going to be given by this quantum Fourier transform multiplied with x. Now, this basis, which we're going to look at, is our new computational basis, which typically is given by 0, 0, which we relabel as 0, 0. Then we have 0 tensor product with 1, which we relabel as 0, 1. Then we have 1, 0. Sorry, 1. Let me see if I can squeeze it in properly with 0. So this is 1, 0. And finally, we have 1, 1 tensor product with 1. And this is the state which we label as 1, 1. Now, these states, the way we have labeled them here, is not as convenient as we would like to have it. So what we're going to do is to remap everything in terms of binaries. So let's take a look at this representation here. So what we are going to do now is to have a more compact notation. So that means that this state, and I'm going to mark this with red, is going to be labeled as state 0. This will be state 1. This will be state 2. And this will be state 3. So how do we do this mapping when we know the values of these bits here? Okay. So we are going to make an ordering now. And this ordering, just keep this in mind, this can be changed. So I'm going to write a state like y. For this qubit 2 example, this will contain one of the qubits, which I call for Y0 and Y1. So as an example, suppose we look at this state, which is 0, 1. Now I can rewrite this in terms of an integer binary representation. Now, many of you have seen the end product, where I'm actually using a binary float representation. That's the final answer, which we are going to derive. However, I want to go through this more, how to say, pedagogical stepping, in the sense that I start with an integer binary. Now, keep in mind that you could also have the other order. So I could start with this one and Y0. We are coming back to that. But if I choose this kind of binary representation, then this specific state, which I've called for Y, and I'm going to translate into numbers, is now going to be given by 2. So we will start with n minus 1 Y0 plus 2 of n minus 2 of Y1, and plus all the way up to 2 to the power of 0 of y of n minus 1. You could interchange. So if you interchange the ordering, like we've done here, you would obviously start with the first one. No, with the highest one, sorry. So for this specific case, if we now look at the n equal 2 case, then this y is equal to 2 to the power of 1 times y0 plus 2 to the power of 0 times y1. This should be 0, not 6. Okay? So that means that if I put now y0 equal to 0 and y1 equal to 1, that means that this y becomes equal to just 1. And this is the labeling which I put here. So I just call this 0, 1 for state number 1. If I have 0, 0, then this just translates into 0 if I use this formula here. So what I'm doing is actually to set up a bit encoding of the 2-qubit states. I have 4 states, but I'm going to just renumber them. And I need to have a recipe which allows me to translate from the single qubit basis, which is given by these individual qubits, which you have here. So the states are just the tensor products of these individual qubit states. And you will quickly see that if you do n equal to 3, you will get a similar recipe to translate the states. So for that specific state here, when y is equal to 0 and y1 is equal to 1, then y becomes equal to 1. So that means that this 0, 1 maps over to state 1. And it's pretty straightforward to see if I take 1, 1, that maps over to 3. And where this 3 is simply 2 to the power of 1 of y0, and this is equal to 1, plus 2 to the power of 0 times y1, which is equal to 1. And obviously this one becomes equal to 3. Okay? So you can quickly see that if you have 3 qubits, this mapping applies as well. So let's do an example just as a small digression. Example 3 here. And then we take n equal to 3. And that means that we have n equal to 8. And then we will have states like 0, 0. That would be one of the states. We would have 0, 0, 1. We would have 0, 1, 0, etc., all the way up to 1, 1, 1, like that. And these are states, these states which you see here are now tensor products of 3 qubits. So the reason why I'm doing this is that we are going to rewrite the Fourier transform as a set of tensor products in terms of the individual qubits. And that means that the Fourier transforms are just going to be given by different rotation matrices applied to each single qubit. And you see now immediately here, supposing I take this specific state, if this is a y we want to find, this would be 2 to the power of 2 times y0 plus 2 to the power of 1 of y1 plus 2 to the power of 0 of y2. So in this case, this is equal to 0, this is equal to 0, and this is equal to 1. So that gives us simply state 1. So it means that this state is then mapped into state 1. This is mapped into state 0. And you will then see that when we proceed, the final state will just be state 7. Okay. So if I now look at the 2-qubit case, let's go back to that one. And we are going to write this in terms of just the Fourier transform without thinking of a qubit basis representation. So let's go back to the n equal to 4, which means that we have 2 qubits. So in that specific case, a state j, the way we are going to transform it, is going to be 1 over square root of 4, which is 2. And then I'm going to have j equal to 0. And this goes up to 3, which is the same as 4 minus 1, n minus 1. And I'm just setting up the formula 2 pi of I times j divided by n and multiplied with y. So the states which we have here are these 1 qubit states. Now, what you would find then is that this matrix U, if you look at this expression for the 2 qubit case, is going to be equal to, as we set up before, 1, 1, 1. But we are going to have 1 of I minus 1 and minus I. So when we set in all the coefficients, and 1 minus I, 1 minus I. So I hope I'm writing this correctly. Minus 1 and then I. So if I look at the state 0, 0, and how that gets transformed, so what I would get then, if I look at the new state, so if I act with this QFT on, so the 0, 0 state, so this is going to be given by the following. So I'm going to have 1 over 2. So this is actually us looking at a state which is 0. If I look at this one, so j equal to 0, that is going to be given by the following. So I will have 0. If I take this formula here, so that means I'm going to have this row here, which is then multiplied with the original basis. So I'm going to have plus 1, plus 2, plus 3, which is actually the same as 1/2 multiply with 0, 0, plus 0, 1, plus 1, 0, plus 1, 1, like that. And if I set it up, this is going to be equal to 1/2 of 1, 1, 1, 1, like this. And if I look at it differently, I can actually rewrite this as 1/2 multiplied with 1. And I can break it down in terms of 2 qubits, 2 pi of j divided by 2 to the power of 0 and tensor product with 1 of e of 2 pi of I. So I is just imaginary. J divided by 2 to the power of 1. So if j is equal to 0, as we had in this specific case, then these are just ones, all the exponentials. And so if j is equal to 0, which we had here, so this specific case here, then these translate simply into just 1, 1 tensor product with 1, 1, which gives us this final result. Now, what I've done here is actually something which I have anticipated. And you don't see that immediately from the basic Fourier transform. So what I set up here is nothing but what we did before the break, without thinking of rewriting this in terms of single qubits. So here I just took the states which I have defined. So I have defined this state, 0, 1, etc. I plug them into the formula, and then I find the new basis. And that means that the 0, 0 state in the new basis is then a linear combination of 0, 0, 0, 1, 1, 0, and 1, 1. So that's the Fourier transform for that specific state. But I can actually rewrite it in this strange way here. So let's see how that comes through, okay? So keep in mind, this formula here, this is the one we started with. That's just the definition of the discrete Fourier transform. So let's take a closer look here at this more compact notation here. So let's, if we now look at this notation which we had, so let's take a basis J. This is state, the number which we are recovering from the qubits is 2 of n minus 1 plus J1 of 2 of n minus 2 plus all the way down to J of n minus 2 of 2 to the power of 1 plus Jn minus 1 of 2 to the power of 0. And in this specific case, that means that a state like 0, 0 is mapped into the state 0. For the 2 qubit case, the state 0, 1 is mapped into number 1, 1, 0 is mapped into 2, and 1, 1 is mapped into 3. So the numbers J's, which you see here, are actually these numbers, okay? But then, based on the qubits which we have here, we can actually recover that information. Then we have the other basis. So we have another state, K, which has the same formula. So we would have a K0. So we are making a transformation from a basis K to a basis J, like you saw in here, right? Here I just labeled, sorry, I should actually have labeled this as a, so I have an I. Yeah, sorry, this, I should have called this for K, and there should have been IJK here. Sorry for that. I had overseen that one, I saw that. Now, okay, so I have a 2 to the n minus 1. So the same coding, K of 2 of n minus 2 and all the way down to K of n minus 1, and then multiply with 2 to the power of 0. So what I have then is a state like J0, J1 up to Jn minus 1, which is then equal to this state which we just labeled J. And similarly, I have a K0, K1, and these are tensor products. Keep that in mind, eh? And this is equal to a given state K. Now, I can actually rewrite this if we now look at the mapping when I perform the Fourier transform. So this specific Fourier transform, which I have, is now given by 1 over 2 to the power of n half. But I can now perform a sum over the individual qubits. So I can have a sum over K0, which then just takes the value 0, 1. So these are the possibilities. So this is just a mapping of the formula which you saw here, this one, in terms of the 2 qubit case. Now the single qubit case. So I would have a K1, which can then be given by 0 and 1. And this goes all the way up to Kn minus 1 equal 0 and 1. These are the values which it can take. multiplied with E of I of 2 pi multiplied with J, and then I have a sum here of M equals 0 of N minus 1 of Km of 2 to the power of minus M, and this is multiplied with this states K0, K1 up to Kn minus 1 here. I can rewrite this in a more compact way as follows. So this is something which I can now rewrite as a K0. There is a factor of 1 over 2n². There's a sum over K, and the sums now over these K0s and K1s, etc., runs only over the qubits which we have. This computational basis with 1 qubit. And this is runs up to Kn minus 1 equals 0 and 1. And this is multiplied with a tensor product where I have M equal to 0 up to N minus 1 of E I of 2 pi of J of K multiplied with Km, sorry. And this is divided or multiplied with 2 to the power of minus M. And keep in mind now that these Km's take only values 0 and 1. And this is multiplied with Km here, like that. So it means that what we have then, when we put this up, is that this can be rewritten as 1 over 2 to n². And then I have the tensor product of M equals 0 to N minus 1. And then I have a sum over Km, which only takes values 0 and 1, of E of I of 2 pi of J of Km divided by 2M multiplied with Km here, this state. And if we go back to the 2 qubit case, what we have then with N equal to 2, if we look at that one, then if we have a state like J1, this is given by 1/2, and then I have 0 plus E of I 2 pi, and then I have 0 multiplied with 0 multiplied with J0 divided by 2 multiplied with 1, and tensor product with 0 plus E of I of 2 pi, and then I have again I would have I have J1. Now this should be, wait, I have actually did something wrong here. Where did I? E of, I got lost in the jungle of all the indices here. Let me just, where did I? So there's one index which is wrong. That should be, now that's J0. It should, that was the wrong one. It should be just pi times J0. And this is 2i, 2 pi, J1, and this is divided by 2 to the power of 2 multiplied with 1. That's the way it should look like. So that's for the 2 qubit case. So we have a compact expression, and this expression here, when we now write it out, when we look at this 0, 0, that simply becomes 1 over 2, and then I have 0, 0, plus, because then I have J0 equals 0, and J1 equal to 0. So that gives me simply 0, 1, plus 1, 0, plus 1, 1, which we had before. You can try different other combinations with 3 qubits, etc., as a small exercise. But the thing now is that this notation which you see here can actually be changed. So if you look at what we have here, we actually have a divided by 2. So instead of us using an integer representation, we could now look at a binary float representation. And then we could get a more compact expression for these terms, because we could then take these terms here and rewrite in terms of binary floats instead of binary integers. So let's do that. So let's do that as the last thing. So binary floats instead of binary integers. And the advantage then is that we can get rid of this operation with J1 divided by 2 here and just rewrite it in a more compact way instead of binary integers. So you will find everything which you see here, you will find that in the lecture notes as well. So all these derivations, I just wanted to specialize to the case of some 2 qubits just to show you the example on how we actually proceed now. So with binary floats, the way we could actually write it out, and this depends on the order which we choose. So we could now set it up instead of, so what we had now is the binary integers. Let me just quickly remind you of that one. So this y is equal to y0 of 2 of n minus 1 plus y1 of 2 of n minus 2, etc., all the way down to n minus 1 of 2 to 0. So that was the binary integers. But then we could replace that one with binary floats, where we now could set up a formula like this one. So we have a state which is y equal to y0, y1 up to yn minus 1. So if I look at the n equal 2 case, I could now define a binary float where this one is equal to y1 divided by 2. And then I would have 0, y0, y1, which is then given by y0 divided by 2 plus y1 divided by 4. And you're probably familiar with that formula. So suppose you have a formula like this one of yk plus 1 all the way up to some yn minus 1. This is something you could translate into yk of 2 to the power of minus 1 plus yk minus 1 of 2 to the power of minus 2, and all the way to the final one, which would be y of n minus 1. Let me just switch page here. Or and we get plus, and the final one would then be yn minus 1 multiplied with 2 to the power of n minus k. I assume you've seen formula like this before, right? So instead of us carrying with us this j squared, now j0 divided by 2, j1 divided by 2 to the power of 2, we can actually rewrite this one now in terms of a binary float. So if I now look at my state, what I could do, if I now look at this n equal 2 case, which we had here, so we would then have y1 divided by 2, y0 divided by 2. Let's now take a state y, which we label as a y0 and y1. So that means that what I will get then is that my state, when I perform this transformation, which is equal, so let me just write it like this to indicate that I'm performing the transformation. This is equal to 1/2, and then I have my qubit 0 plus e of 2 pi I, and then I have 0 multiplied, so this 0.1 is actually the binary float representation of 1, and tensor product with 0 plus e of 2 pi I, and then I have 0, 0, 1, and 1. And when I plug in the values which I had, if I now am looking at y0 equal y1 equal to 0, then clearly what I have to plug in is simply 0 divided by 2, 0 divided by 4, and then 0 divided by 2 here, and that would give me back the same expression which we had before. So this is a slightly more compact way by which we can now represent these types of qubits. So when I now look at this, if I look at my 2-qubit case in general terms, you see now that I have one here, which is going to be given to give us a Hadamard gate. But then this one, depending on the value of 0 and 1 here, will in general be represented by a rotation gate. So for the 2-qubit case, if we summarize a little bit, so for 2 qubits, what I will see then, if I look at these expressions which I put up, is that I will have an expression where on the first qubit, we have a Hadamard gate. So this is exactly the same as he had for the 1-qubit case. And the second qubit, the second one, is affected by a rotation gate. Affected. And we are coming back to next week how the circuit is going to look like. So I was hoping to get that today, but I will have to postpone that to next week. One, and the second one is affected by a rotation gate. And so this is roughly where we will stop today. And next week, we are going to write down the circuits for the 2-qubit case and the more general case with more than 2 qubits. And the whole trick now is that we have rewritten everything in terms of operations with specific gates, like Hadamard gates and rotation gates, instead of performing a matrix-matrix multiplication, which is what you would set up if you have a discrete Fourier transform. So this recipe, which you see here, instead of us simply doing u times a vector x, we are now going to translate that one into operations on single qubits. And each one of these operations is going to represent a specific gate. So the first one is going to be given by a Hadamard gate, and the rest one are different rotation gates. And next week, we are going to look at how we can encode this. And when we have done that, we are going to look at the quantum phase estimation algorithm, which is based on the quantum Fourier transform. So I just wanted to go through some of these basic mathematical aspects, which is actually us, if we go back a little bit, instead of setting everything up like this, which then can be translated into a matrix acting on the state, we're actually breaking this down in terms of single qubit operations, which are then given by an expression like the one which you see here. And that's the big benefit compared with a traditional discrete Fourier transform. So keep in mind this expression here, that encodes for the 2-qubit case, the simplification from multiplying with this one to actually operating on the computational basis of 1 qubit, 0 and 1. So next week, the idea is to enlarge this to more than just 2 qubits. So now we just focused on this simpler case here. So we are going to take this recipe, which you see here, We are going to expand it to more qubits. We're going to look at what circuits look like. And then we're going to write a code which implements the quantum Fourier transform in terms of gates and not matrix vector multiplications. And with that, we can move on to the quantum phase estimation algorithm, which will allow us to extract eigenvalues of a given Hamiltonian. And that will conclude roughly the part before the break. And then after the break, we are going to discuss quantum machine learning algorithms and perhaps other algorithms as well. Okay, I'm going to stop here